Welcome back. In the previous lecture, we had looked at how nuclear science, nuclear physics, nuclear chemistry originated. In this lecture, we will give a direction how it has evolved and where we are. So, if you remember, interest in phosphorescence, fluorescence was very critical in the way nuclear science originated. Although the scientists who were exploring this field were interested in fluorescence and phosphorescence, the reason for the radiation is not actually fluorescence or phosphorescence. So they were looking at uranium, let's say uranium 238, and uranium gives rise to a variety of radiation because uranium transforms to different elements along the trajectory. There can be a variety of radiations, alpha radiation, beta radiation, and gamma radiation, till this these elements transform to a stable nucleus. So, for example, if you start with U238, they will follow this trajectory till the nucleus transform to this stable element. So one of the goals for this course is to understand all the possible transformation. And as you can also see that there is a lot of difference in the half-life of different elements. Some have a very small half-life, some have very large half-life. So some of these features would be expanded and explained as we progress along the course. Another important thing to notice is that uh, when an element transforms from uh, one atomic nucleus to another atomic nucleus, both the atomic number in this reaction and atomic weight in this reaction will be conserved. We will see this again and again. Like the way you can think about this is there are rules for balancing a chemical reaction. Likewise, there are rules for balancing a nuclear reaction. The fundamental rule is that the sum of the atomic number and is from the reactants is the same as the sum of atomic number of the products. Likewise, the sum of the atomic weight of the reactant is the same as the sum of atomic weight of the products. We'll see these things with certain examples. So there are different uranium is not the only element that transform. There are different nuclear transformation that are possible. The main thing is that all these things will transform till they reach a stable nucleus. So there are a couple of questions you want to be answering. Why are these elements not stable, and why is, let's say, lead stable? Not everything is radioactive. Why are some elements radioactive and some others that are not radioactive? What are the rules and patterns that are that determine the reasons for radioactivity? So we'll look at this in the next few lectures. So there are different species, this actinium species and so on. They're denoted by certain terminologies is 4n+1 series. We will see why it is so called. Um, all of them end at a stable nucleus. So there are compared to heavy elements, there are also other light elements which also disintegrate. For example, if you have potassium 40, they would also they are also radioactive, um, and this gives you sort of a table on just to show you that there are a variety of radioactive elements with a variety of half-lives and so on. But many of them are the isotopic abundance, for example, of potassium, radioactive potassium is quite less. If you take a particular naturally occurring potassium, it will also have some amount of radioactive potassium, but the abundance of this radioactive atomic nucleus of potassium is much less. So there are some critical experiments in radiochemistry. We will chart out some of them, and in the next lecture, we'll elaborate a lot more experiments so that you get an understanding of the trajectory that has been followed in nuclear physics and nuclear chemistry. So many of you might have heard about Curie's law of magnetism. That was not established by Madame Curie. It was established by her husband, Pierre Curie. So Curies were very important in the development of radio chemistry in the early days of radiochemistry. What they found was that they saw that the uranium ore is more radioactive than uranium. So this can probably suggest a particular feature. Supposing that when you say it is an uranium ore, what do you mean by that? In addition to uh, uranium ore has some other impurities, right? So if the uranium ore is more radioactive than uranium, you can infer that the impurities in uranium ore is more radioactive than uranium itself, right? So that was the important inference they made. So this important aspect of experimentation, that is, it is important not only to see, but you have to observe. Okay, so observation is something more than just seeing. So they observed that uranium ore is more radioactive. From that observation, they inferred that the uranium ore has some other element which is more radioactive than uranium. So they were trained in chemistry, so they use certain separation techniques that are common in those days of chemistry, and were able to purify this uranium ore. The purification led to the identification and new discovery of new elements, polonium and radium. So this aspect of nuclear science has more to do with nuclear chemistry, because the techniques that were utilized in the purification and identification was more common of chemistry than nuclear physics. So Marie Curie also was able to, via experiments, get to the atomic weight of radium. So just imagine, these are in the early stages of nuclear science. So you should try to pause and think, how did she get to the atomic weight of radium? What kind of experimental procedures were available which facilitated her to get to the atomic weight of radium? Just pause and think for yourself before you progress. So the way she did that was using molten or fused salt electrolysis. Again, you should pause and think why this kind of experimental technique would have allowed her to get to the atomic weight of radium. So all she had with her was Faraday's law. So this is a very good utilization of Faraday's law to Faraday's laws of electrolysis to get to the atomic weight of radium. So you should go back and look at how what is Faraday's laws of electrolysis, how that would have helped her to find out the atomic weight of radium. So in the next lecture, we would give the trajectory followed in nuclear physics and chemistry via the different Nobel Prizes that were awarded in nuclear physics and nuclear chemistry. So this will give you a bird's eye view of how nuclear science evolved. That's we won't go into the details of each Nobel Prize, but we'll quickly go over the different Nobel Prizes so that you can get a big picture view of how this field evolved and where we are right now. Thank you.